Thank you all for joining us today for a webinar on sensors and actuator design using IntelliSuite. We are excited to have you here. My name is Abdul Qadir Hassan Qureshi, and I'm a team lead of MEMS Nanofabrication and Integration Group at CMC Microsystems. So we are honored to have Dr. Sripath Raja with us today, and we sincerely appreciate him sharing his insights with our audience. Dr. Sripath Raja is Manager of Application and Sales at IntelliSense Software. He is responsible for the development of business for MEMS software package IntelliSuite. He has about over 10 years of experience in design, fabrication, and development of MEMS devices using IntelliSuite. He holds his PhD from National Institute of Technology, Karnataka, India. In this webinar, we will explore in detail on how IntelliSuite software can be beneficial and help through various verticals of MEMS development cycle.
Okay, so this webinar is on the sensors and actuators design using IntelliSuite software, and it's hosted by CMC Microsystems, as all of you know. Okay, so today let's explore how IntelliSuite software can really help understand or help in design the MEMS devices in a seamless process. Probably in the interest of the bandwidth, probably I'll switch off my camera for a while. I think that should make that should accommodate, right? Okay, yeah. So probably I can switch it on during our interactions later. Right, okay, so going ahead. So here we have an outline of what MEMS devices, probably I would not take much, few seconds on it, and challenges in the MEMS design and development, a complete cycle, a structural design and process optimization in the EDA, and the research opportunities that we have with MEMS simulations. Okay, so as all of us know that the MEMS is a integration of mechanical parts on a silicon substrate, and it uses a CMOS and a bipolar bi-CMOS technology for manufacturing. And we have the micromachining process, which makes it different from the conventional CMOS IC fabrication process. And it's an emerging technology and also promising, and typical scale is from 1 micrometer to 1 millimeter. And we have lots and lots of application coming forward. So in various different segments and various different verticals, aerospace, biomedical, automotive. So we have lots of sensors and actuators are required moving forward with AI coming in, IoT coming in place. So sensors will be the focus of development for the next 10, 15 years. We have a lot of sensors that can come on the table. So one of them is the MEMS sensors, where IntelliSense can play a big role in developing them. As a sensor development, what we generally do is, anyone for that matter, we collect the design requirements, we do the basic design, and we will do the optimization. So this is the typical workflow of the MEMS design. So how do we adopt this methodology into our software is that we do a 3D model of it, and then we perform a lot of multiphysics simulations. Further, we do a reduced order model simulation, what we call it as the ROM, and we have the SME, system model extraction, and system level integration, everything within the software. Once the device is optimized, then we have the layout that we create on the blueprint module, and we define the process recipe, try to optimize the process recipe. In case if you are following a certain PDK, then we can optimize the process recipes with specific to PDK. Process optimization includes the process steps, mask optimizations, so all of those things. Further, it gives a lot of feedback on how the fabrication can be done or with minimum iterations. And then finally, the device will be fabricated and tested. So this is the typical life development cycle of MEMS devices. And we play a role in optimizing most of the microfabrication stuff, the system integration, and the multiphysics. So all in all, it's a complete MEMS simulation processes. So further, if we divide the MEMS design, we have three categories. So one is the multiphysics simulation. I would always start with that because process or the microfabrication comes later, only when we optimize the device. So what we generally do is we do a lot of multiphysics simulations with a 3D CAD model without bringing in the process recipe. Once we finalize or once we optimize the device for its multiphysics response, then we can integrate that with EDA. So we can do a lot of system integration within the software, and the electronics can be interfaced here. And once everything is set, we can define the process recipe. If you are a fab engineer or process engineer, you can optimize your processes. If you're a design engineer following a PDK, then fit the PDK here, run your design, and try to find out if you are meeting the design rules of the PDK. So you can do all of these things within the software, which saves a lot of time and effort within the fabrication area. Yeah, so let's further go down. So with multiphysics, what's our approach? So typically in multiphysics, we do a 3D model and then we do a FEM simulation with a lot of parameters. Parameters includes the load parameters like thermal, mechanical, electrical parameters. It can also be dimensional parameters, the change in the material properties. So there are lots of parameters that we consider during the optimization. So for that, what we offer a solution is you parameterize the structural. If you wish to explore a lot of design with with incremental change in the structures, so you can define a parametric structure and tell the software that this is the range of dimensions that I'm looking for, and you perform the simulation of this stuff and then throw me the output. So that can be done. And further, the parameterized input variables, I mean, this is quite understandable, is that we give a range of voltage to check the pull-in. We give a range of thermal voltage, thermal load. We give range of acceleration. We give a range of pressure to see the response of the device. So we parameterize the input load. Further, we do a system model extraction and perform a reduced order model simulation for integrating this with electronic circuits. So, and reduced order model simulation also considers a lot of damping effects when we do it. So it's more of a lumped model simulation where it can also verify or help in benchmarking the FEM simulations. We also have PSpice netlist kind of a stuff for element-based models. We drag and drop elements like beams, comb structures, and switches, and some gyroscopes, accelerometers. So we can do element-based model simulations of MEMS devices. We can also parameterize the structural and parameterize input variables. Once all of these things are in place, we try to fabricate the device. So we create a layout, the blueprint layout, and then define the process recipe, and we do the process integration. Further, with undercut, overcut, or surface micromachining issues, we again rework on the layout to meet the DRC. So again, it's in the feedback loop. So to try optimizing the process recipe. So the solution that we have here is please work within the design rules of the foundry that you're working with. Better is to follow the PDK. We have some PDK in our deck, so we can any users of a software can always use that. But in case if someone wants to build a PDK, so we generally help them with their process handbook and then help them to build the PDK within the software. We do the process verification, um, and this is the solution that we offer here in three different verticals. One is the FEM, the multiphysics. We do a lot of parametric simulations. On the system model extraction, we do the element-based modeling and reduced order model simulation. And on the process recipe, we optimize mask layouts, we optimize the process recipe, and finally do the process integration. Okay, so it's a fast field multiphysics simulation. So here we have the thermal, electrical, mechanical, piezoelectric, piezoresistive, magnetostrictive kind of simulations that can be done within the software. So these are some of the examples that we have. A few nonlinear simulations can also be possible. So this is an interesting example. Probably, I think I should use a pointer here. Yes. So here, this is a resonator. So we do a reduced system model extraction and then put this to a black box, a reduced ordered model simulation, and we connect the onboard IC or the electronic components to process the signal and synthesize the signal, whatever you want to call it. A board level electronics can be designed within the software. Okay. This is an example of thermal packaging. So what really happens after the packaging stuff is done? What really is the device response can also be checked through. So the benefits that we have with this 2D and 3D modeling basically is without using the process recipe, without using the process models, is that the entry point for FEM device is through a 2D layout and converted to 3D or direct 3D models. And it saves a lot of time with parametric simulations. And we do a lot of post-processing for better visualization. And we do a reduced order modeling, which is the Lagrangian or the lump model output, which helps us to verify or benchmark to validate the FEM simulation. Yeah, so basically it's element-based models. We do drag and drop of these elements like beams, plates, comb structures, and then try to integrate them like a circuit and build MEMS devices out of it. And it saves a lots and lots of time. It's 1,000 times faster than FEM simulations. Okay, and if, we can also get the output in the 3D form. Yeah, so let me jump on to the microfabrication. The four major steps in microfabrication is the deposition, lithography, etching, and bonding. Different materials, different processes, different steps, different etching methods, different types of masks, various bonding processes. So the name it, you get it. Okay. So yeah, so this is an overview of what the software is all about. So let's go further down with through the process through the FEM simulation again. So here let's take an example of a MEMS accelerometer. I mean, this is just a proof mask connected with 4 beams here. And we want to see the natural frequency change with change in the beam length. So here I can define or tell the software that this is the range of length, width, or the thickness that I want to see the change in the natural frequency. Please do it for me. So it does the simulation, which generates a lots of model and repeats the simulation on all of the model, and then throws an output which helps uh, to have a better clarity on how the device responds and helps in freezing our device dimensions as early as possible. So the same similar case for a comb structure or a capacitive type of device and a piezoelectric beam as well. So we do a system model extraction. What we generally do is we capture the strain energy associated with each modes of vibration. In case if it's an electrostatic model, then we capture the electrostatic energy and we capture the fluid damping characteristics like the viscous damping uh, effects, and then we integrate them into a HDL file and then push this to a reduced order model simulation. So this is just a representation of how a reduced order model simulation would look like. This element is called the macro model element, where the HDL file is dumped on this element, and this device works exactly like our FEM model and then throws the output in various signal forms, and the signals can further be taken and processes, synthesis, and try to trigger some of the circuits at the subsequent stages. So the outcome of this one is more reliable and it can be benchmarking, because here we compare the lump model with FEM. Okay, and we have a comprehensive study where by doing a lot of parametric simulation, we get a better idea of the structural behavior for behavior of the device for range of loads. If we have more data, it's always easy or it's beneficial to have uh, to target any specific applications. Okay. Yeah, so we have the element-based models. We'll just quickly run through this. So we have lots of elements. We drag and drop them. We create a lot of device like gyroscopes, accelerometers, resonators, and things like that. And we can also do a parametric simulation of the element-based model. And parametric simulation based on the ambient conditions. You can see in the graph number 2, it's of pressure. With the change in pressure at the ambient condition, how the response would change. Okay, so that's something that's possible with element-based modeling. So the outcome is typically a simulation which is static, frequency, and dynamic. The results are generally ideal unless we really define the damping conditions properly. With respect to element-based models or the reduced order model simulation, we define the ambient conditions like the mean free path of the molecules, the pressure around the device, the the viscosity of the gas around it. So that really helps in deciding the damping factor internally. And this helps us to keep our expectations closer to a real-time fabricated devices. Okay, so at this point, we are at a juncture where we have seen lots of devices, and let's jump on to MEMS fabrication, the clean room stuff. So there are two ways of looking at it. One is what is off the shelf, which is available. what's the software contains and how it can really benefit the MEMS community worldwide. Is that if we have a template where the MEMS processes or various PDKs are integrated within the software, and if you wish to do a custom process, then then you can also use the software to define your own process recipe. If we have a lot of material database, and it can be exported to Excel and PowerPoint for better clarity and better communication. So here, the process templates that we already have in place is the MEMS process, soy MEMS, piezo MEMS, metal MEMS, poly MEMS, and we also have the Polaris process, which is from GE, which is typically used for navigation applications, gyroscope device. So we worked with a GE few months ago, and we have the PDK within our software. And we have the Scream and Summit. And these are a couple of PDKs that we already have. So and it's open for anyone, any user to use this. Okay. In case if you are into custom process, then we have the process definition done, and we can define your own process recipe to optimize your process. Okay, so let me quickly on this file. Yeah, probably. Yeah. So here, the short video, what you saw is a combination of various etching processes, especially the DRI, on a nano hole array, which is typically an optical waveguide kind of a structure. So what you see on the left panel, on the left image, is the process recipe, various steps that we have adopted, and the animation is the simulation of this process recipe step. So we can push this, the process recipe into PowerPoint, whatever the structure that you have, they keep it at a particular view and then push this. So you really do not have to prepare a presentation to explain your processes. Okay, I mean, this comes in handy for most of the academic people where they'll require lots and lots of documentation. Okay. And moving further, we have the bulk micromachining. The bulk micromachining is all about atomistic level simulation. So we can also plan to do a lots of etching at atomistic level to unit cell of silicon. Let me take this example here. It is a 100 plane, 150 minutes of etching, 1110 plane, 30 minutes of etching, and 111 plane with 1500 minutes of etching. So here, all of them goes through this. Probably, I think have to enable this video. Probably, and we can help me. Oh, yes, I got it now. Right. Okay, so here what we see is how the profile looks like. Okay, so what's the profile that is achieved with KO Hedge with 150 minutes of etching on a 100 plane? And what really happens with 30 minutes of etching with KO Hedge as an etchant with on a 110 plane? So this study can be done to optimize your wet etching parameters. And all of these parameters or all of the results are based on experimental database. If you are using TMAH, you can as well use it with the TMAH with a combination of Triton, KOH plus IPA. So these are some of the standard steps that we already have built in. So we can tell you what's the profile looks like when you really do the simulation. So here is the case of TMAH. The same mask, we use it on a quartz substrate. Can also do quartz based simulation or the wet etching for quartz, AT cut, Z cut. How does the profile looks like? So this will help in optimizing the process and also optimizing the mask. So this is a good example of how the same mask can be used for achieving various edge profiles like the isotropic edge, anisotropic edge, and the plasma etching. So various shapes can be achieved, and based on that, we choose the etching parameter. So this is an example where we see a KOH etching, KOH plus IPA, TMAH, and TMAH Triton. So what are these basically? So this is the surface profile that is achieved with a square shape mask. Okay, so when it's with IPA, this is the profile. It's with Triton, this is the profile. Triton and TMAH combination, and this is the profile that we have. Yeah, moving further is to try to create an octagon structure on a silicon 100 wafer. So here I'm trying to show you is that the plus shape mask is used to create an octagon structure on a silicon 100 wafer. So what I'm trying to tell you is that you can do a lot of mask optimization within the software to achieve the desired profile of the device. The same thing on a silicon 111, we are using a mask which is a two triangle meeting at a point, and you can see our octagon structure can be created or an octagon edge profile is created, and with further etching it becomes a hexagon. So most of you are aware that there is something called as etch stop or etching time. So beyond that or anything less, so it really changes the profile that we really wanted. So it helps in optimizing your process recipe. Similarly is the case with INP, indium phosphide material. So those who are working in the photonics space will typically use INP, right? Further, we have the quartz where you can see that the desired profile or the profile that looks when we use same mask on a different orientation of quartz. Let me jump into the last parts of it. Okay, so until here, is what we have things off the shelf. Okay, so this is a general capabilities of the software. Further, we generally also receive lots and lots of requests from our users, from new prospects, uh, to have some things that really help them. So we really develop some of the capabilities to them, sometimes exclusively, and if the NDA allows us to give this outside, probably we may also share this. So based on the commitment and the exchange of thoughts, we have developed a few additional features as well. So this was developed for one of the big defense company, uh, the wafer level based simulation. Or what they really wanted to know is the edge profile at the wafer level. So what we were just doing is at the die level. So what they anticipated is that at the wafer level, the edge profiles are different. So we anticipate a lot of changes. We wanted to simulate and see how the profile looks like. So then we developed a recipe for that, and a 3D lithography, grayscale lithography. So this is for OE Solutions in the US, and we developed this, and this is how it looks like, a 3D or the grayscale lithography. So we have developed this, and further is the etching of sapphire material, wet etching of sapphire, and the spray etching on copper. And generally, even probably this would be much manual nowadays, is that the number of dies that can fit in the wafer based on the footprint of the device and the dicing area. So just it predicts that the number of devices that fits within the wafer. And this was recently developed for one of our prospects, the XeFE2 gaseous released. So how does it look before and after the edge profile looks like? So recently, for one of the big players, we helped them to build ion beam lithography simulation and thermal oxidation process. Like they just wanted to know the silicon ratio on how much it is being consumed when it's on the sidewall, when it meets. So various different levels of understanding. So as I said, with the process recipe or the micro fabrication stuff, we work in two things. Like one is off the shelf, you're free to use it, and few of them are exclusively developed based on the our commitment policy that we have. Okay, so so further we develop a lot of multiphysics simulation. So this is an example of an array-based simulation, a parametric simulation for an array in the multiphysics. Define the process recipe, define the piezo-resistive parameters based on the process that you have adopted. You are doping a p-type in an n-type semiconductor or an n-type in a p-type semiconductor. So based on that, at what temperature do you define and what is the depth of for the implant. So based on that, the piezo-resistive coefficients, the pi11, pi44, gets decided. So we can also define the process recipe as well. Process parameters for the boron implant, or we can straight away define the pi coefficients directly. Well, so moving forward, we also achieved some of these things with integration with 180 nanometer. So this is a snapshot shared by one of our users that he was able to integrate with the Cadence tool, the integration of Gyro with his testing IC in Cadence. He was exploring 180 nanometer technology. So he's been doing that. So we have some stories, some good stories to hear from our users who really do the integration process between MEMS and CMOS. Okay, so I'm coming to the end of my talk, and we have discussed a lot of things on different things on the multiphysics, different things on the microfabrication and the system integration.